Welcome to Everyday Mathematics. Today we are moving forward to the second part of the MIT Integration B qualifying exams that took place yesterday, the 20th of January 2026. And we'll be looking at the last 10 problems, 11 to 20. And this is problem 11, problem 12, problem 13, problem 14, problem 15, problem 16, 17, 18, 19, and 20. So we'll go step by step and solve each problem and then end the video. So without much ado, let's jump into the solution phase of this video. Problem 11 says, what is the value of a definite integral from x equals -1 to +1 of the maximum between 0 and the square root of 1 minus x squared minus a half? So what is crucial here is to see that we have an x squared there, which means that this problem is symmetrical about 0. So in other words, this problem is the same as twice the integral from 0 to 1 of the maximum value between 0 and the square root of 1 minus x squared minus a half. So the crucial part here is to know that point for which this value starts being maximum or stops being maximum with respect or when compared to 0. So let's say 1 minus x squared minus a half greater than 0 means that the square root of 1 minus x squared is greater than a half. And that means that 1 minus x squared is greater than a quarter. And that means that 1 minus a quarter is greater than x squared. And that means that 3/4 is greater than x squared. And which means that when x is less than root 3 over 2, this value holds. So in other words, since we've come to a point where our integral is this means that that's the same as twice integral from 0 to root 3 over 2 of 1 minus x squared minus a half plus so this one here goes to 0, and so we are left with twice the integral from so that's our integral. Now, since this is we could choose to use substitution where we say let x be equal to sine theta, such that dx d theta is equals to cosine of theta, and therefore dx would be equal to cosine of theta d theta, right? And then when x is equals to 0, theta would be equal to 0. When x equals to root 3 over 2, theta would be equal to pi over 3, right? And therefore our problem becomes twice, integral from 0 to pi over 3 square root of 1 minus sine squared theta minus a half cosine theta d theta. So this here becomes cosine theta. We have cosine of theta here. 1 minus sine squared theta is cosine squared theta, square root as cosine theta. So we have that, which is twice 0 cosine squared theta minus a half cosine theta. Now, since cosine 2 theta is the same as twice cosine squared theta minus 1, using this identity, we can now substitute for that. So we have this becomes cosine 2 theta plus 1 over 2 minus a half sine theta here. And so this goes with that. And we have cosine 2 theta plus 1 minus cosine theta. And so we have a half sine 2 theta plus theta minus sine theta 0 pi over 3. Since our problem has brought us to a half sine 2 theta plus theta minus sine theta 0 pi over 3 is the same as half sine of 2 pi over 3 plus pi over 3 minus sine pi over 3 minus half of 0 plus 0 minus 0. So this here is sine over 2 pi over 3 and sine of pi over 3, so this is 3 root 3 over 2, and this is also root 3 over 2. And so we have root 3 over 4 here plus pi over 3 minus root 3 over 2. Okay, which is equals to pi over 3. And so common denominator, this becomes minus okay. So in other words, our integral from negative 1 rather to positive 1 of the maximum between 0 and square root of 1 minus x squared minus a half equals to pi over 3 minus root 3 over 4. And that, ladies and gentlemen, is our answer. So problem 12 is a definite integral from x equals to 0 to x equals to 1 of the square root of x squared plus the square root of x squared plus x plus the square root of x squared plus x, and so on and so on. So what we could do is we could substitute and say let this part be equal to y. So if we say let y be equal to the square root of x squared plus x plus the square root of x squared plus x plus square root of, that means that when we square both the right hand and the left hand side, we have y squared being equal to x squared plus x. Notice this is also y, and so we have x squared like that. So and so y squared minus y is equals to x squared plus x, and I could say that y minus a half squared minus a quarter is equals to x plus a half squared minus a quarter. And this cancel out. In other words, y squared is equals to, okay? So we've gotten ourselves there. Well, now, since x is greater than 0, and we see that y minus a half squared is equals to x plus a half squared, we could just say square root of both sides, and therefore dy dx is equals to 1, and therefore dy is equals to dx. When x equals to 0, so from here we see that y is equals to x plus 1. Okay, so when x equals to 0, y equals to 1. When x equals to 1, y equals to 2. And so what we see is that our problem, which is x squared plus x squared plus x plus square root, is equals to 1 to 2 y dy, which is equals to y squared over 2 integrated 1 to 2, which means we have 2 squared over 2 minus 1 squared over 2, which is 4 over 2, which is 2 minus a half, which is 3 over 2. And so this complicated problem that seemed intimidating initially is equals to 3 over 2. And that, ladies and gentlemen, is our answer. So problem number 13 looks a little bit intimidating, which is the indefinite integral of cosine x to the power 5 minus 10 cosine to the power 3x, cosine of x to the power 3 times sine x squared plus 5 cosine x times sine to the power 4 of x. This is interesting, and we're going to try and rewrite this in a little bit more easy to understand. So we have this cosine to the power 5x minus part of this, we shall bring here. We have cosine x to the power 3, or cosine cube x, sine squared x, and then we shall keep 4 and you will see what we're trying to do here in a minute. And then so we have -1, -4, and then we have -5, and all of that comes to this -10 times sine squared x, and this is plus 5 cosine of x sine to the power 4 of x. Okay, so let's combine that for a minute. So we have pull out cosine cube x, and we have cosine squared of x minus sine squared of x. Okay, then we have 4 cosine of x squared, sine squared of x, and then I have remained with cosine of x here, so that this and this become cosine cube x. And then we have, combining this and that, I can pull out 5, and we have cosine of x sine squared of x, and so inside the bracket I have cosine negative here, cosine squared of x plus sine squared of x. Okay, so this here is the same as cosine of 2x, and this here becomes not this, but with this here we have sine squared 2x, and then here we have negative cosine 2x. So our problem now becomes cosine cube x times cosine of 2x minus sine squared 2x cosine of x minus 5 cosine of x sine squared of x times cosine of 2x. Okay, so we are making inroads there. The next thing we could do is we could bring one of this side. So we can say that this is the same as cosine cube of x cosine of 2x minus cosine of x sine squared of x cosine of 2x minus sine squared 2x cosine x minus 4 cosine of 2x cosine of x sine squared of x dx. Okay, so let's write this in a way that is easy to understand. So we have the integral of cosine cube of x times cosine of 2x minus cosine of x sine squared 2x cosine of 2x minus sine squared of 2x cosine of x minus 4 cosine of x sine squared of x cosine of 2x dx. Okay, so focusing on this part, we can pull out cosine of x and cosine of 2x. And so we are left with cosine squared x minus sine squared of x. And apologies, we might have made a small mistake here. There's no 2 there. So it's just sine squared of x. And then we have here, we can pull cosine of x out. But no, let's just keep things the way they are for now. Sine squared 2x cosine x minus 4 cosine x sine squared x cosine 2x. So this is the same as cosine 2x. So we have cosine of x. And so here we have cosine squared 2x minus sine squared 2x cosine of x, which is this one here, minus 4 cosine of x sine of x cosine of 2x. Okay, this is our next target, but also we can pull this out so that we have cosine of x cosine squared 2x minus sine squared 2x minus 2 sine 2x cosine 2x. And I think we are missing one thing here. So this is squared here. We miss our squared there. And so we have sine of x there. So this here is the same as cosine 4x. So we have cosine of x cosine of 4x, and this here becomes sine of 2x, so we have as 4x rather, sine 4x, and then we have sine of x. Okay, so since our problem now has, this is better, and we know that cosine rather that cosine of a plus b is equals to cosine of a cosine of b minus sine a sine b, which is a key identity here, which means that we have cosine of x plus 4x, which is equals to cosine of 5x. And this really is a half sine of 5x plus the integration constant. So that's actually our answer. Yeah, it's just too much. But that's what was being looked for. So without much ado, let's go to our next problem. Number 14 is the indefinite integral of the arctangent of the square root of x. Okay, this is interesting. My quick intuition is to say let u be equal to these arctangent of the square root of x, which means that tangent of u is equals to square root of x, and therefore tangent squared of u is equals to x. So therefore secant squared u twice tangent of u du dx is equals to 1. And so we can substitute for that way. Okay, so the integral arctangent, and we said let u be equal to the arctangent of the square root of x, and we've come to a point where we say 2 secant squared over u tangent of u du can be used to substitute for dx. We've come to that point. That means that if this is u, our integral becomes u secant squared of u tangent of u du, which means that we have u times the derivative of. So using integration by part, where if you have a product of function v and the derivative of function u integrated, we have uv minus the integral of u times the derivative of v, such that if this here is our u and this here is our v, then our problem becomes u tangent squared of u minus tangent squared of u, derivative of u is du. Okay, so we've come to a point where we have u tangent squared of u minus now we know that 1 plus tangent squared of x is equals to secant squared of x. Our integral now becomes secant squared of u minus 1. And here, this is a famous integral. This is the same as tangent of x, so we tangent of u, so we have tan squared of u minus tangent of u integrated minus u. 1 integrated is u plus the integration constant. So we've integrated our problem to tangent of u plus u plus the integration constant. But we said u is equals to the arctangent of square root of x, right? That means that our integral is where there is u, we have arctangent of square root of x. Tan squared of that, we get x minus tangent of u is square root of x, and then u is the same as arctangent of square root of x plus the integration constant. Now pull everything out, we have 1 plus x arctangent of the square root of x minus square root of x plus integration constant of c. So rather now our problem now is 1 plus x arctangent of square root of x minus square root of x plus c. And that, ladies and gentlemen, is our answer. So problem number 15, which happens to be a definite integral from x equals to 0 to x equals to 1000 of the floor of the ceiling of x, the ceiling of the floor of x, the floor of the fractional part of x, the fractional part of the floor of x, the ceiling of the fractional part of x, and the fractional part of the ceiling of x. These are very interesting things. So let's define these functions. What is the ceiling of x? The ceiling of x is equal to integer k plus 1 when x is less or equal to k plus 1 and greater than k. So when that real number x lies between those two integers, the ceiling of x takes the upper integer if it's bounded within that region. Then if we have the floor of x is equals to k when x is less or equal to k, is greater or equal to k and less than k plus 1 rather. Now the fractional part of x is equals to x minus the floor of x, meaning that it is that extra fraction of the real number on top of the integer right below it. So in other words, the fractional part of x lies between 0 and 1. It's never 1. It's between 0 and less than 1. So let's try to interpret our problem here. Okay, so suppose it, let's look at this for example here. If we split this into domains, and we have k starting from 0 and would go all the way to, let's say, 999, because we are limited right at 1000. So this is the same as the floor of k plus 1 in each region, plus the ceiling of k plus the floor of x minus the floor of x, which is k, which is k here, plus the fractional part of k, and then we're here, plus the ceiling of x minus k plus the fractional part of k. And now we are integrating all these from k to k plus 1, right? Now another thing to note is since this here is an integer, the fractional part of that will be 0. And then since this is a fraction, the fraction of the ceiling of that will be 1. And we're looking at this, sorry, this is k plus 1, and this is k. So the fractional part of an integer will be 0, and the floor of the fractional part, since this lies between 0 and less than 1, so this becomes 0, and these are all integers. So in other words, our problem becomes very soon integral from k to k plus 1, or we can just pull these integers out, and then plus k plus 1. And these are all constants, so we can pull everything out. Two k plus 2, right, which is equals to the summation from k equals 0 to 999 of 2k plus 2. Okay, so that's where we've gotten our cells. So why have we decided to express it that way? It's because if you look at an arithmetic progression from k equals to 1 to k equals to n of k, that's the same as capital N over 2 times n plus 1. So we've used this formula. So now our problem, which is twice k from 1 to k equals 1000 of k, is equals twice 1000 divided by 2 times 1000 plus 1. And this cancels, so we have 1,001,000, and that is our answer. So so we have problem number 16, which is definite integral of the square root of cosine of x times cotangent of x times cosecant of x over sine of x times tangent of x times secant of x. So let's just express all these things in terms of the primary trigonometrical function. So cosine of x in the numerator is the same as cosine of x. Cotangent of x is the same as cosine of x over sine of x. And cosecant of x is the same as 1 over sine of x. Now, sine of x is the same as sine of x. Tangent of x is the same as sine of x over cosine of x. Secant of x is 1 over cosine of x. So we see here that our problem now is the same as cosine squared of x over sine squared of x over sine squared of x over cosine squared of x. Right, so which is the same as square root of cosine to the power 4 of x over sine sine to the power 4 rather. So which is equals to the same as cosine squared of x over sine squared of x. Cotangent square of x. And then what is cotangent of x? Since 1 plus cotangent squared of x is equal to cosecant squared of x, our integral is the same as the integral of cosecant squared of x minus 1. Okay? So we said our integral is cos x squared of x minus 1. We know that when we differentiate cotangent of x, we get cos x squared of x, right? Negative. So this means our integral rather is negative cotangent of x minus x plus the integration constant. So that's our answer without really thinking any further. So problem number 17, which is the definite integral from x tending negative infinity to x tending to infinity of e to the power negative x squared over 1 plus e to the power 2x. A couple of things. Let's try to invert this. So let's say let u be equal to negative x such that du equals to negative dx. And so this becomes infinity we have 1 plus e to u negative du. This becomes, with this negative sign, helping us invert the limits. And so this is so what this is telling us is that is the same as that's what this is telling us. And so what we can say here is that if I is our integral, so we have I, 2I is equals to plus right? So which is equals to and so this is and we see that this and that would cancel, so we are left with a Gaussian integral. So if our 2I is equals to, and this here is the same as root of pi, then I is equals to square root of pi over 2. And therefore, our initial integral is equals to root of pi over 2. That's our answer. So problem number 18, which is the indefinite integral of sine squared of x over x squared minus sine 2x over x. This is the same as, let's try to expand this out so that things seem a little bit visible there. So we have minus 2 sine x cosine of x over x. So this part here is the same as the derivative of this. And what I see here is this part here is the same as the derivative of this as well. So I have sine squared x times the derivative of negative 1 over x plus negative 1 over x times the derivative of sine squared x. Okay, and this is the derivative of a product. And so what this is telling us that this is the integral of the derivative of negative 1 over x sine squared of x. And an integral being an antiderivative means that we have 1 over x sine squared of x plus the integration constant. And this, ladies and gentlemen, is our answer without much further thought. So problem number 19, which is a indefinite integral of the natural logarithm of x times the natural logarithm of x over x and natural logarithm of x, which is too nested, but I think our strategy here is to substitute, and we can say let u be equal to natural logarithm of x, which means that du dx is equals to 1 over x, which means that du can be used to substitute dx over x. So we have already seen that there's an x here in the denominator and we have a dx there. So our problem becomes log of u, log of u, du over u. Okay. Then we could also say let y be equals to the natural logarithm of u, which means that dy can be used to substitute for du over u. And as we can see, we have u there and we have a du there. So our problem becomes, this becomes y, and then we have log of y dy. So y, let's delete that. Y natural logarithm of dy, of y rather, is the same as the derivative of y squared over 2 times the log of y. And we're going to use integration by parts, right? Such that this here is our u, this here is our v. And so we have a half y squared log of y minus a half y squared. Derivative of log y is 1 over y. So this and that cancel. So we've come to a half y squared log of y minus a half y, which is a half y squared log of y minus a quarter y squared plus the integration constant. Since y is equals to log of u, this becomes a half log of u squared log of u minus a quarter log squared of u plus c. But again, u is equals to log of x. Then that means that where we have a half log squared of u log of u minus a quarter log squared u c. This is equals to a half log squared of log of x log of x minus a quarter log squared of log of x plus the integration constant. We can pull a couple of things out. We can pull this out, and so this becomes a quarter log squared of log of x, and we are remaining with twice log of x minus 1 plus the integration constant. And that, ladies and gentlemen, is our answer. So problem 20 is the definite integral from x equals 0 to x equals pi over 2 of cosine squared of pi over 2 times cosine squared of pi over 2 times cosine squared of x. So this function, first of all, cosine squared x is continuous within this region of integration, which means that this is also continuous, and this is continuous between, so this 0 to 1, and so the entire function, if we call that function fx, is existent and continuous within the region of integration, and so without loss of any, since there are no discontinuities, it's just safe for us to say if this is our integration and we say let u be equal to pi over 2 minus x, this means that du can be used to substitute for negative dx, and when x is equals to 0, u equals to pi over 2. When x equals to pi over 2, u equals to 0, meaning that this integral is the same as integral from pi over 2 to 0 of f and because we have a negative sign here, we can flip the limits without losing anything. So this is our problem, and so what that means for us is that our integral from 0 to pi over 2, the integral of fx, is the same as 0 to pi over 2 f pi over 2 minus x, which means that 0 to pi over 2 of cosine squared pi over 2 cosine squared pi over 2 cosine squared of x is equals to the same integral pi over 2 cosine squared pi over 2 sine squared of x. Okay, which means that is the same as pi over 2 1 minus cosine squared of x, which allows us to, since cosine of a minus b is equals to cosine of a cosine b plus sine a sine b, since we have that means this, now since we have our problem here, which is cosine squared pi over 2 cosine squared of pi over 2 of sine squared of x is the same as 0 pi over 2 cosine squared. We can express this as 1 minus cosine squared of x. So we have pi over 2, 1 minus cosine squared x. And using the identity that we introduce, we have cosine pi over 2 cosine of pi over 2 cosine squared of x plus sine pi over 2, and we have sine of pi over 2 cosine squared x, and this goes to 0, so we have this is 1, so we have rather, and there's this squared that goes to that, so we have cosine pi over 2 cosine x. Okay, so our problem 0 to pi over 2 has become cosine squared pi over 2 sine squared pi over 2 cosine squared. And this propagates, you can just clearly see that this becomes quickly sine squared pi over 2 cosine squared pi over 2 cosine squared x, right? And so, in other words, our initial integral 0 to pi over 2 cosine squared pi over 2 cosine squared pi over 2 cosine squared of x is equal to sine squared pi over 2 cosine squared pi over 2 cosine squared of x. And that means that our 2I is equals to plus right, which using the identity of sine squared x plus cosine squared x equals to 1, this is the same as integrating 1, which is x from 0 to pi over 2. So 2I is equals to pi over 2 minus 0. Therefore, I is equals to pi over 2 divided by 2, which is pi over 4. And so the very complicated integral of cosine pi over 2 cosine squared pi over 2 cosine squared of x is equals to pi over 4. Okay, so that actually brings us to the end of this series of the qualifying exams of the MIT Integration B 2026 that happened yesterday. Today we'll move on to the regular season. We'll do some quarterfinals tomorrow, semifinals, the days to come, and then the finals. So if you have any questions, don't hesitate to reach out to us via the comment section. But also you can email us and we'll be able to clarify any steps that may seem not clear. So thank you so much for your attention. Thank you so much for always hanging out with us. If you haven't subscribed to our channel, we do encourage you to consider subscribing to our channel. And yeah, let's grow together. Until next time, bye-bye.